In the deep, silent space between the stars, the journey was ending. An object, born in the fire and ice of an alien solar system, was nearing the end of a voyage that had lasted for millions of years. It had crossed a chasm of unimaginable size, a hostile ocean of radiation and cold. Against all odds, it had arrived intact, a messenger from a world we will never see. We called it 3I/Atlas. When we saw it, we were astonished it had survived the journey at all. But the truth was far stranger. The real mystery was not its survival. It was its profound and impossible fragility. Tonight, we explore a cosmic paradox, the story of a traveler that should have been shattered by the journey, but was instead saved for a gentle and baffling death in our own backyard. We journey into the mystery of why 3I/Atlas should never have survived. Before we can ask how it survived its impossible journey, we must first witness its death. For the story of 3I/Atlas is not a story of immense strength, but of a profound and deeply unsettling weakness. Its final moments in our solar system are not just the end of its life, they are the key to understanding the paradox of its entire existence. When it was first detected in the final days of 2019, it was just another faint smudge on a digital photograph, one of thousands of new objects cataloged by our automated sky surveys. For weeks, it behaved as expected. A comet, falling in from the outer darkness, it grew steadily brighter as it approached the sun. By March of 2020, it was putting on a spectacular show, its brightness increasing so rapidly that astronomers predicted it could become a brilliant naked-eye object, one of the great comets of a generation. Hopes were high. This was only the third interstellar visitor we had ever identified, and it was promising to be the brightest and most revealing one yet. And then, the show stopped. In the third week of March, its brightening stalled. Then, it began to fade. The decline was catastrophic. Over the course of just a few days, its brilliance plummeted by a factor of more than 100. The celestial jewel had shattered. The Hubble Space Telescope was turned toward the fading ghost, and what it saw confirmed our fears. There was no single solid object anymore. There was only a loose, elongated chain of icy fragments, a string of pearls drifting apart in the darkness, each piece a tombstone marking the death of a visitor from another star. Imagine finding a perfectly preserved ancient scroll, written in an unknown language, that has somehow washed ashore after crossing a vast, storm-tossed ocean. You are astonished that a thing so delicate could have possibly survived the waves and the wind. But then, as you carry it inside and place it under the gentlest of museum lights, you watch in horror as the ancient parchment simply crumbles into a fine gray dust. This was 3I/Atlas. It had apparently survived millions of years in a cosmic storm, only to dissolve in the gentle, warming sunlight of our inner solar system. This baffling death is the first half of our great paradox. Let us consider the scene of the crime. The disintegration began when ATLS was approximately 145 million kilometers from the Sun, almost the same distance as the Earth's own orbit. For a comet, this is the temperate zone. The Sun's heat is still a relatively gentle force here. Comets from our own solar system, born and bred in the chaos of our own neighborhood, are tough. They routinely survive passages far, far closer to the Sun, whipping through the inferno of the inner system and emerging with their tails blazing. Comet Halley, for example, travels well inside the orbit of Venus, to a distance of just 88 million kilometers from the Sun, and it has been doing so for millennia. The death of Atlas was not only premature, it was also remarkably gentle. The Hubble images showed that the fragments were drifting apart at a leisurely pace of just a few meters per second, the speed of a brisk walk. This was not a violent explosion, not the result of a pressurized pocket of gas blowing the comet to smithereens. This was a quiet, almost lazy, crumbling. It was as if the object was held together by the weakest of cosmic glue, and the slightest rise in temperature had caused that glue to simply evaporate, letting the constituent pieces drift away. It did not shatter like a rock. It dissolved like a sugar cube in warm water. This was the evidence laid before us. A visitor from the stars, dead on arrival, not from a catastrophic collision, not from a violent explosion, but from a mysterious and deeply ingrained inherent fragility. It was, it seemed, one of the most structurally weak and delicate objects we had ever witnessed. And this is where the mystery truly begins. This profound weakness is completely at odds with the story of its journey. To understand the second half of this paradox, we must now rewind the clock. We must trace its path backward, not just out of our solar system, past the orbits of Jupiter and Saturn, but out into the vast, hostile, and unforgiving wilderness from which it came, an interstellar wilderness that it should have never, ever survived. The space between the stars is not empty. We call it a vacuum, and for our human scales, it is. This is a lie of language, a failure of our imagination to grasp the true nature of the cosmos. Over the immense time scales and distances of an interstellar journey, this so-called emptiness is revealed to be a thin, invisible soup of matter and energy, a realm of constant, relentless hazards that can grind down even the hardest of worlds over the eons. For a fragile snowflake like 3I/Atlas, this ocean should have been a furnace. Any object traveling through the galaxy must endure a gauntlet of two primary unending assaults. A first is a form of invisible fire, a rain of high-energy particles that comes from all directions at once. These are the galactic cosmic rays. They are the nuclei of atoms, mostly protons, the hearts of hydrogen atoms, that have been stripped of their electrons and accelerated to nearly the speed of light. They are fired from the magnetic hearts of exploding stars, supernovae, the greatest cataclysms in the universe. For millions of years, they travel the galaxy, a form of radiation so powerful and penetrating that it can alter the DNA of living creatures and wreak havoc on solid matter. Galactic cosmic rays are like a steady, unending drizzle of microscopic, hypervelocity bullets. A single one of these bullets might not do much to a mountain-sized comet, but if that comet is exposed to a constant, patient rain of these bullets for 10 million years, the damage becomes immense. It is a form of celestial erosion, a radiation sandblaster. Each particle that strikes the comet penetrates deep into its icy surface, depositing energy and breaking apart the delicate chemical bonds that hold the ice and dust together. Water molecules are split, methane is destroyed. The very structure of the ice is weakened, made brittle and porous. Over a journey of millions of years, this cosmic radiation is a relentless agent of decay, slowly tenderizing the comet, weakening its internal structure from the inside out. The second assault is a more direct physical one. It is an erosion not of radiation, but of matter. The interstellar medium is not a perfect vacuum. It is filled with a thin, diffuse gas of hydrogen and helium, and a sprinkling of tiny microscopic dust grains. The density is incredibly low, just a few atoms per cubic centimeter. But the comet is not sitting still. It is plowing through this medium at an incredible speed, perhaps 30 kilometers per second, or 70,000 miles per hour. Imagine driving a car through what seems to be a light, gentle fog. Now imagine you are driving not at 60 miles per hour, but at 70,000 miles per hour. That gentle fog is no longer gentle. It becomes a relentless, high-energy barrage against your windshield. Each tiny water droplet is a microscopic impact, a tiny explosion of energy. This is what an interstellar comet experiences. The seemingly empty space in front of it becomes a storm of microscopic shrapnel. Each tiny dust grain it collides with, even one smaller than a grain of sand, hits with the explosive energy of a firecracker. Each hydrogen atom it plows through is another tiny impact. This is a process called sputtering. It is a physical sandblasting, a constant bombardment that kicks atoms and molecules directly off the comet's surface, stripping it away, layer by patient layer. Over the course of a multi-million-year journey, this process can be devastating. It is estimated that a typical interstellar comet could lose meters, or even tens of meters, of its surface material to this constant high-velocity erosion. For a small comet, just a few kilometers in diameter, this could be a death sentence. It could be completely vaporized before it ever reaches another star system. This is the gauntlet, a relentless bombardment of cosmic ray radiation, slowly cooking and weakening the comet from the inside, and a constant high-speed sandblasting from interstellar dust and gas, eroding it from the outside. Any object that survives this journey should be tough. It should be weathered. It should be the hard, dense, surviving core of a much larger body. And yet 3I/Atlas arrived in our solar system as a ghost, a thing so delicate, so loosely bound, that it could not even survive the gentle caress of our sun's warmth. How did this celestial snowflake survive a cosmic firestorm? How did a structure with the integrity of a loosely packed snowball endure a journey that should have blasted it to dust? This is the central mystery that baffles astronomers. This is the paradox that challenges our understanding of how these interstellar visitors are born, how they travel, and how they die. And it is the question that lies at the very heart of our journey tonight. To solve the riddle of an impossible journey, we must begin at the source. An object's strength, its resilience, its very ability to exist, is determined by the conditions of its birth. If 3Psi/Atlas was a celestial snowflake, then we must ask what kind of impossibly gentle, impossibly serene cosmic cloud could have ever formed it. When we look to our own solar system for a comparison, the paradox only deepens. For in our home, the birth of a comet is an act of profound and terrifying violence. The standard model of our solar system's formation is not a gentle ballet, it was a cosmic demolition derby. In the beginning, there was a vast spinning disk of gas and dust around our young sun. Within this disk, trillions of small icy bodies, the planetesimals, began to clump together. This was a chaotic era of constant brutal collisions. But the true violence came with the birth of the giants. Jupiter, with its immense gravity, was the neighborhood bully. It grew to its colossal size by consuming countless smaller bodies, its gravity well acting as a monstrous vortex. But for every world it consumed, there were thousands more it merely terrorized. Its gravity acted as a colossal slingshot, grabbing the small icy comets and flinging them with unimaginable force. Most were sent careening into the sun or into the other growing planets. But many were thrown so hard that they were ejected from the solar system entirely, cast out into the interstellar void. The comets that survived this violent upbringing, the ones that now reside in our distant Oort cloud, are the tough ones. They are the survivors of the demolition derby. They are the celestial equivalent of rocks that have been put through an industrial rock tumbler for 1 billion years. They have been gravitationally battered, collisionally processed, and hardened by the chaos of their youth. They should be dense, compact, and structurally sound. And for the most part, they are. They are built to last. 3I/Atlas, by contrast, seems to have been assembled in a quiet, celestial clean room. Its utter fragility, its inability to survive even the gentle warmth of the inner solar system, suggests it was born in a place without a Jupiter, a place without a cosmic bully. It hints at a serene, almost placid solar system, where the process of formation was not a chaotic battle, but a gentle accumulation. Perhaps it formed in a disk of gas and dust that was exceptionally cold and quiescent, where the ices could condense slowly and delicately, like frost on a window pane, creating a low-density, fluffy structure. But this creates a new and profound problem. How did it get here? To be ejected from its home star system, an object needs a powerful gravitational kick. It needs a giant planet, a Jupiter or a Saturn, to act as the slingshot, a serene, gentle solar system. The kind that might produce such a fragile comet would likely lack the very engine needed to send it on an interstellar journey. It is a cosmic catch-22. The conditions required to make such a delicate object are the very conditions that should prevent it from ever leaving its home. The paradox of its existence has now doubled. Not only should its multi-million-year journey through the interstellar gauntlet have destroyed it, but its very birth and ejection from its home star system seem to be a physical contradiction. It is a ghost from a place that, by our understanding, shouldn't be able to produce interstellar travelers. It is a message sent from a post office that should have no mail trucks. This deep, seemingly irreconcilable mystery has forced astronomers to consider more radical, more exotic possibilities. It has forced us to step back and ask a fundamental question. We have been assuming that 3I/Atlas was a comet, a primordial dirty snowball, just like the ones we know. But what if it wasn't? What if its fragility is not a sign of a gentle birth, but a sign that it is a different kind of object entirely? When a mystery becomes this deep, when the conventional explanations begin to break down, a detective will look for similar cases, for other anomalies that might shed light on the puzzle. 3I/Atlas was not the first interstellar visitor to baffle us. Its story, and the story of its impossible fragility, is now forever intertwined with the first and strangest of its kind, Pioneer, the enigma that has haunted planetary science since its brief flyby visit in 2017. The object known as Oumuamua was a mystery from start to finish. It was small, perhaps only a few hundred meters long, and it was tumbling through space in a way that suggested a bizarre, highly elongated shape, like a cosmic cigar or needle. Unlike a traditional comet, It showed no fuzzy coma of gas and dust as it passed by the sun. It appeared to be a dry, inert, rocky object. But its greatest mystery was its motion. As Oumuamua began to leave our solar system, our telescopes tracked its path with incredible precision, and they found it was not following the path that gravity alone had dictated. Something was giving it a tiny extra push, a gentle but persistent acceleration away from the sun. For a normal comet, this is easily explained by outgassing, the rocket-like effect of ice turning to gas. But Oumuamua had no visible outgassing. It was a ghost engine, pushing an object for no apparent reason. This puzzle has led to a host of theories, including one particularly elegant and compelling idea that may solve the mystery of both Oumuamua and 3I/Atlas. What if Oumuamua was not made of rock and not made of water ice, but was instead a fragment of a much larger Pluto-like world and was made almost entirely of solid nitrogen? Imagine a block of dry ice, frozen carbon dioxide, sitting on a smooth floor. As it warms, it doesn't melt into a puddle, it sublimates, turning directly into a layer of invisible carbon dioxide gas underneath it. This gas acts as a lubricant, allowing the block to glide around almost frictionlessly. The outgassing is powerful, but it is completely invisible. A pure nitrogen iceberg, born in the deep absolute zero freeze of another solar system, would behave in exactly the same way when it entered the relative warmth of our own. The solid nitrogen on its surface would turn into invisible nitrogen gas, creating gentle, undetectable jets. These jets would be the ghost engine that gave Oumuamua its mysterious push. So, how does this connect to the fragile ghost, 3I/Atlas? What if Atlas was also one of these exotic icebergs? Perhaps it was not made of pure, solid nitrogen, but of another, even more delicate, highly volatile ice, an ice like solid carbon monoxide. Carbon monoxide freezes at an even higher temperature than nitrogen, but it is still what we call a supervolatile. An object made primarily of carbon monoxide ice would be incredibly fragile, with a structural integrity far, far weaker than that of a comet made from water ice. And crucially, it would begin to sublimate, to fall apart, at a much greater distance from the sun. The gentle warmth near Earth's orbit, which a water ice comet would barely notice, would be like a furnace to a solid block of carbon monoxide. It would begin to fizz and crumble with an almost explosive force. This theory offers a tantalizing, almost perfect solution to the paradox of Atlas's death. The reason it was so fragile, the reason it dissolved so easily and so far from the sun, is because it wasn't a comet in the way we have always understood them. It was a different kind of beast entirely. It was a fragment of an alien world, made from an exotic frozen gas. This would explain its profound weakness. But in solving one mystery, it opens another, even more profound question. What kind of solar system produces, and then shatters, entire worlds made of frozen nitrogen and carbon monoxide? For a century, we have thought of comets as primordial relics. We have called them dirty snowballs, the leftover building blocks, the scraps and shavings left on the cosmic workshop floor after the planets were assembled. They are baby pictures of a solar system's birth, but the strangeness of Oumuamua and the impossible fragility of 3I/Atlas are now pointing toward a new and far more violent possibility. What if the interstellar highway is not filled with leftovers, but with shrapnel? What if these visitors are not baby pictures, but autopsy reports? What if they are the shattered pieces of fully formed and now long dead worlds? This is a radical shift in perspective. It begins with a process called differentiation. When a large planetary body, like a dwarf planet the size of Pluto, forms, the heat from its formation and from radioactive elements causes it to melt. As it melts, the materials separate by density. The heavy rocky materials sink to the center to form a solid core. The lighter materials, the ices, rise to the top, but not all ices are the same. Water ice, being relatively dense, might form a thick solid mantle, but the most volatile, lightest ices like solid nitrogen, methane, and carbon monoxide would form a thick frozen crust on the very surface. Think of a planet like a layered gourmet chocolate. It has a dense, nutty core, a thick layer of caramel, and a delicate frozen outer shell. Now, imagine a catastrophic impact in that alien solar system. Another large world strikes this layered planet with unimaginable force. The impact is like hitting that gourmet chocolate with a hammer. The The pieces that fly off will not all be the same. Some will be dense, rocky chunks from the nutty core. Some will be mixed pieces of the core and the caramel mantle. And some will be incredibly fragile, light shards of just the outer frozen shell. The interstellar visitors in this model are this planetary shrapnel. They are the fragments from these world-shattering cataclysms. And this model beautifully explains the wild diversity we have seen in just our first three guests. The second visitor, 2I/Borisov, which looked and acted just like a normal comet from our own solar system, could be one of those classic primordial bodies, a true leftover that was ejected before the planets were fully formed. Oumuamua, the strange rocky-looking object with the ghost engine, could be a shard from the nitrogen ice crust of a shattered alien Pluto. Its journey of millions of years through the cosmic ray gauntlet would have cooked its surface, breaking down the nitrogen ice and leaving a dark, reddish, carbon-rich crust, making it appear rocky, while the pristine, volatile ice remained hidden just beneath the surface, ready to power its escape from our sun. And 3I/Atlas, our fragile ghost, could be a different kind of crustal fragment, perhaps a piece from an even colder world, one whose surface was dominated by the most delicate and volatile of all ices, solid carbon monoxide. It would be a piece of the thinnest, most delicate part of the candy shell. This is a breathtaking and terrifying vision of our galaxy. It implies that the space between the stars is filled with the debris of planetary destruction. For every solar system like our own, which has settled into a state of relative peace, there may be another that suffered a far more violent fate, a system that tore itself apart in a series of catastrophic collisions, seeding the galaxy with the broken pieces of its dead worlds. This theory seems to explain the fragility of 3I/Atlas. It was not a primordial snowball, it was a delicate shard of an ice shell, but in doing so, it presents us with a new and perhaps even more difficult survival paradox. How could a piece of a fragile, icy crust possibly survive the very cataclysm that shattered its parent world in the first place? The hammer that can shatter a planet should not leave behind delicate, intact snowflakes of its crust. The mystery of its survival has now been pushed back to the moment of a violent and seemingly impossible creation. The story of any celestial object is written in its light. For centuries, we have known that if you pass a beam of light through a prism, it will split into a rainbow of colors, a spectrum. But if the light has first passed through a gas, that rainbow will be scarred with dark lines, a cosmic barcode that reveals, with unerring accuracy, the chemical elements within that gas. When astronomers turned their spectrographs to the faint, fuzzy atmosphere of 3I/Atlas, they expected to read the familiar story of a comet. Instead, they found a story that was deeply perplexing, a story defined not by what was there, but by what was missing. A typical comet from our own solar system is a well-stocked pantry of cosmic ingredients. Born in the cold, outer darkness, it is rich in the universe's most common and vital materials. Its primary component is water ice, but mixed in are generous portions of frozen carbon dioxide and carbon monoxide, methane, ammonia, and a host of complex carbon-based organic molecules. When a comet like this approaches the sun, these ices turn to gas, and its spectral barcode clearly shows the strong signatures of all these parent molecules and their fragments. We know this barcode by heart. The spectrum of 3I/Atlas looked like a pantry that had been raided. The signature of water was there, certainly, but the most vital carbon-based ingredients were almost entirely gone. Astronomers searched for the barcode of carbon monoxide, one of the most common molecules in the cold clouds where comets form, and found almost nothing. They looked for the signature of diatomic carbon, two carbon atoms bonded together, a common fragment in cometary atmospheres, and found that it was profoundly depleted. It had a tiny amount of cyanide, a molecule of carbon and nitrogen, but far, far less than a normal comet of its size. To put this in perspective, for every 100 molecules of water detected in a typical comet's atmosphere, we would expect to find 10 or 20 or even 30 carbon-bearing molecules. In the atmosphere of 3I/Atlas, the ratio was closer to 1. This was not a small, subtle difference. This was a fundamental chemical anomaly. It was a recipe for a world, but with one of the most important ingredients inexplicably missing. How could this be? This profound lack of carbon makes it very difficult for Atlas to be a primordial object, a leftover from the birth of its solar system. The clouds of gas and dust that form stars and planets are universally rich in carbon. For a comet to form, with almost none of it, is like trying to bake a loaf of bread without any flour. But this strange chemical fingerprint makes perfect sense if we abandon the idea that it was a primordial comet. If instead it was a piece of shrapnel from a large, differentiated, Pluto-like world, then its chemistry is not a mystery, it is a clue. A large, layered world would not be chemically uniform. Its different layers would have different compositions. The deep, rocky core would be rich in silicates. The mantle might be mostly water ice, and the outermost crust could be formed from the condensation of the most volatile gases, like nitrogen or carbon monoxide, creating a layer that could be, by its very nature, extremely poor in carbon. The weird, anemic chemistry of 3I/Atlas could be a direct chemical fingerprint of the specific carbon-poor crustal layer of the shattered alien world from which it was torn. Its chemical signature was as fragile and strange as its physical structure. It was not a dirty snowball, rich in all the universe's common ingredients. It was something specialized, something refined, something that could only have formed in a very specific layer of a much larger and much more complex world. But this only seems to dig the rabbit hole of our paradox even deeper. Our visitor now appears to be a highly specialized, chemically unique, and structurally delicate piece of a larger parent body. How could such a specific and fragile thing possibly survive the interstellar gauntlet? The answer may be the most counterintuitive of all. Perhaps it survived not in spite of its weakness, but because of it. We are faced with a seemingly impossible contradiction. A profoundly fragile object that has survived a profoundly brutal journey. The logic of our celestial mechanics seems to break down. But what if we are looking at the problem from the wrong direction? We assume that strength and density are assets for survival. But what if, in the strange slow-motion physics of the interstellar void, weakness is a virtue? What if the profound fragility of 3I/Atlas was not a liability? What if it was its greatest strength? What if it was its only shield? To understand this, we must add one more piece to the puzzle of its identity. Let us assume it was not just fragile, but also extremely porous, that it was not a solid, dense block of ice, but a low-density, loosely packed agglomeration of ice grains, a cosmic fluff ball. Its structure would be more like a loosely packed snowball than a solid ball of ice, riddled with vast amounts of empty space. Now let us revisit the two great hazards of the interstellar ocean. First, the cosmic rays, the microscopic bullets of radiation. In a dense, solid object, a cosmic ray particle deposits all of its energy in a very small, concentrated area, shattering chemical bonds and causing significant structural damage. It is like a bullet hitting a pane of glass, sending spiderweb cracks through the entire structure. But in a very low-density, fluffy object, a cosmic ray is far more likely to pass straight through, encountering very few atoms and depositing much less energy per unit of volume. The damage it does is localized, less concentrated, and far less structurally catastrophic. Second, let us consider the physical sandblasting from interstellar dust. An impact from a micrometeorite on a hard, solid, brittle body sends a powerful shockwave through the entire object. A large enough impact can propagate fractures that shatter the whole thing. But an impact on a fluffy, porous body is like punching a pillow. The energy of the impact is absorbed and dissipated locally. The impact might vaporize a tiny puff of the comet's material, but it does not send a catastrophic shockwave through the body. It cannot shatter a structure that is barely a structure at all. Imagine trying to destroy a solid block of wood with a sandblaster. The constant stream of sand will pit the surface, erode the edges, and slowly but surely grind the block away. Now, imagine trying to destroy a cloud of smoke with the same sandblaster. The sand will simply pass through it. The cloud is too diffuse, too ethereal, too fluffy to be effectively destroyed by the impacts. An extremely porous comet would behave more like the cloud of smoke than the block of wood. This is a beautiful and profoundly counterintuitive idea, that in the face of a relentless million-year bombardment, the best defense is not a heavy shield, but a body made of almost nothingness. 3I/Atlas may have survived its journey because it was a cosmic fluff ball. It would have lost mass, certainly. The sputtering and erosion would have stripped away its outer layers, one molecule at a time. It would have survived by sacrificing its own body to the void. It would have arrived in our solar system as a shadow of its former self, its outer protective layers completely stripped away, its core structure weakened and exposed by the long journey, primed and ready for the final gentle nudge from our sun that would cause it to completely disintegrate. This theory elegantly solves the paradox of the journey, but one final piece of the puzzle remains. It explains how it survived the ocean, but not how it got there in the first place. We now have a working theory for the impossible journey, a theory that transforms the weakness of 3I/Atlas into its secret weapon. But the timeline of a comet's life begins not in the silent void, but in the gravitational chaos of its home. We are still left with the problem of the hammer blow. How does a celestial snowflake, a cosmic fluff ball, survive the initial violent act of ejection? How does it survive a gravitational slingshot powerful enough to cast it into the abyss between the stars? The standard model for ejecting a comet is a brutal one. It involves a close, high-speed flyby of a giant planet like Jupiter. In a single, powerful gravitational encounter, the planet grabs the comet and flings it like a stone from a sling, accelerating it beyond its star's escape velocity. For a dense, solid comet, this is a traumatic but survivable event. For a low-density fluff ball, it would be a death sentence. The immense tidal forces during the close flyby, the stretching and squeezing from the giant's gravity, would tear the fragile object to shreds before it even had a chance to begin its journey. So, if 3I/Atlas was this fragile, it cannot have been ejected in the usual way. It must have taken a different path, a gentler path. For fortunately for our theory, such paths exist. They are just far more rare. Think of escaping from the top of a very tall building. The standard ejection method is like being thrown from a top-story window. It is a single, violent, and highly effective event, but not one that a fragile object would survive. But there could be another way. A gentler way. Imagine being passed down carefully from floor to floor by a long chain of people, each one giving you a small, gentle push until you are finally deposited safely on the street below. A delicate, fragile object might just survive this multi-stage escape. In celestial mechanics, such a gentle escape is possible in a solar system with a specific and likely rare architecture. It might happen in a system with multiple well-spaced giant planets. A comet could have a close encounter with a smaller Neptune-sized planet, which gives it a gentle nudge into a higher orbit. In that new orbit, it might then encounter a larger, Saturn-sized planet, which gives it another, slightly stronger nudge. This process could repeat itself over thousands or millions of years. A long, slow cascade of gravitational handoffs, each one adding a small amount of energy, until the comet has finally accumulated enough velocity to escape its star altogether. At no point in this process would it be subjected to the overwhelming, world-shattering tidal forces of a single close flyby with a supergiant like Jupiter. This scenario is far less common, but it is physically possible. And if it is the true story of ATLS's birth, it means that our visitor is not just a clue about the composition of alien worlds, but also a clue about their dynamics. It tells us that it likely came from a very specific and perhaps very rare type of solar system, one with a large family of well-behaved giant planets, capable of gently passing a fragile snowball between them and handing it off to the galaxy. We now have it, a complete, if speculative, biography of our ghost, a fragile, carbon-poor, porous fluffball, born as a shard from the crust of a shattered world in a quiet corner of a rare type of solar system, gently nudged from its home over thousands of years in a multi-stage ejection, shielded on its million-year journey by its own ethereal, cloud-like nature, sacrificing its outer body to the harshness of the void, and arriving in our home as a battered, weakened, and anemic survivor, ready to meet its final, gentle end. This story fits all the baffling facts, but it paints a picture of a galaxy where survival is a far more delicate, complex, and improbable business than we ever knew. Our entire elaborate story of this fragile ghost, its impossible birth, its perilous journey, its baffling death, is built upon a foundation of just 3 confirmed interstellar visitors. 3 data points in the history of the cosmos. It is like trying to understand all the magnificent, varied life in the Earth's oceans by studying just 3 individual fish. Our conclusions are profound, but they are, by necessity, speculative. But this era of scarcity, this age of lone discoveries, is about to come to a dramatic end. A new colossal eye is opening on the cosmos, an eye so powerful it will turn our slow trickle of discovery into a raging, data-rich flood. On a remote mountain peak in Chile, the Vera C. Rubin Observatory is preparing to see its first light. and it is a machine built for discovery on an industrial scale. Its mirror is over 8 meters across, capable of gathering immense amounts of faint light. Its camera is the size of a small car, the largest ever built for astronomy. Every few nights, it will photograph the entire visible sky, creating not just a static map, but a high-definition motion picture of the cosmos. Our current sky surveys are like lone fishermen, each casting a single line into the vast cosmic ocean and hoping for a bite. The Rubin Observatory is like a fleet of industrial trawlers, deploying a single continent-sized net that can sweep the entire ocean every single night. We are about to go from catching one or two interstellar fish a year to catching them by the thousands. The scientific consensus is that once it is fully operational, the Rubin Observatory will discover dozens, perhaps even hundreds, of interstellar objects every single year. We are standing on the shore, having just found our third strange shell washed up from the sea. Soon, a great tsunami of discovery will arrive, and it will deposit a whole beach of these alien artifacts at our feet. This coming swarm will transform the study of interstellar objects from a series of fascinating anecdotes into a true statistical science. With a population of hundreds or thousands of these visitors to study, we can finally begin to answer the big questions. Are fragile, porous fluffballs like 3I/Atlas common, or are they a bizarre rarity? Are dense, rocky, needle-shaped objects like Oumuamua the norm? Or will we find that the vast majority of visitors are simple, predictable comets like 2I/Borisov? We will be able to map their trajectories with unprecedented precision. We can see if they truly come from all directions, a well-mixed galactic soup, or if they arrive in streams and currents, the ghostly debris trails of shredded star clusters, or ancient planetary collisions. We will be able to analyze their colors and their light curves and mass, sorting them into families and classes, creating a true taxonomy of the galaxy's wandering population. The coming swarm will give us the hard data we need to test our wild theories. We will see if the galaxy is truly filled with the shrapnel of dead worlds, or if most visitors are the pristine leftovers of planetary formation. The ghost of 3I/Atlas has given us a tantalizing and beautiful story, a story of gentle ejections and fluffy shields. The swarm will tell us if that story is the truth. But seeing them from afar, even in their thousands, is one thing. The next great leap for humanity will be to leave the shore and to go and meet them. For now, we are cosmic archaeologists. We stand on the safe ground of our own solar system and study the faint, ghostly remains of visitors who have already come and gone. We analyze the faint light from their dissolving bodies, and from that, we weave our complex tales. But what if we could become explorers? What if, the next time our new powerful eyes spot one of these mysterious messengers on the horizon, we could launch a ship of our own, chase it down across the vastness of the solar system, and see it up close? This is the Interceptor's gambit, and it is the next great dream of planetary exploration. It is a dream of almost unimaginable difficulty. Chasing down an object that is moving at interstellar speeds on a path that is just barely deflected by our sun is a challenge of celestial mechanics on the absolute cutting edge of our capabilities. It is like trying to jump from a moving car onto a speeding bullet that was fired from a gun half a mile away. Your timing, your speed, and your trajectory must be calculated with a perfection that leaves absolutely zero room for error. The first requirement is time. The Rubin Observatory and other future surveys will give us this, spotting the visitors when they are still far out, years away from their closest approach to the sun. The second requirement is a spacecraft, ready and waiting. We cannot build a mission in response to a discovery. It would be too late. The interceptor must be built, tested, and sitting on a launch pad, or even pre-launched into a stable parking orbit in space, on a hot standby, waiting for the call. And the third, and most difficult requirement, is speed. The interceptor would need to be launched on one of the most powerful rockets ever conceived, and even that would not be enough. To catch its quarry, it would have to execute a complex series of gravitational slingshots, perhaps diving past Venus and the Earth, before taking a final colossal kick from the gravity of Jupiter, flinging it out into the solar system at a velocity that no human-made object has ever achieved. The gambit is immense, the risk is enormous, but the payoff would be a scientific prize without precedent. An interceptor would not just fly by, it would rendezvous. It would match the visitor's speed and fly alongside it, escorting it on its journey through our solar system. For the first time, we would see one of these objects not as a pixel but as a world. We would see the texture of its surface. We would fly through its coma, our instruments tasting its chemistry directly, identifying complex organic molecules that are invisible to our telescopes on Earth. We could watch its jets fire in real time, and perhaps we could even send a small secondary probe to make a kamikaze dive into its nucleus, to give us one final glorious reading of what lies beneath the ancient irradiated crust. We could finally know the truth. Is it a primordial comet? Is it a nitrogen iceberg? Is it a fluffy, porous piece of planetary shrapnel? The interceptor's gambit is the only way to ever know for sure. It is a dream of touching another star system, of analyzing a piece of alien geology in our own hands. It may still be decades away, a project for the next generation. But the journey of 1,000 light-years begins with a single step, and the fragile ghost of 3I/Atlas has shown us exactly which way we need to go. The story of 3I/Atlas, in the end, is not just the story of a single strange object. Its improbable survival and the beautiful complex theories we have had to invent to explain it have painted a new and far more hopeful picture of the galaxy itself. We have journeyed through a tale of paradox and impossibility, but the solution to that paradox has revealed a cosmos that is not just a place of violence and chaos, but a place of surprising subtlety, a place that may be far more hospitable to the creation and transport of delicate things than we ever believed. Dimension was one of brutal efficiency, a violent factory, full of the grinding machinery of gravity and the fiery explosions of supernovae, a place that would naturally produce and transport only the toughest, most hardened pieces of celestial scrap metal. Any delicate structures, we assumed, would be quickly and efficiently destroyed. But the story of a fragile fluffball, gently ejected from its rare and stable home and shielded on its journey by its own ethereal nature, suggests a different kind of cosmos. It suggests that the galaxy might be more like a vast ancient forest than a factory. There are violent storms in this forest, certainly. There are destructive fires and catastrophic collisions. But there are also quiet, protected glades where delicate things like celestial snowflakes can form and grow. And there are gentle, persistent breezes that can carry their seeds for immense distances without utterly destroying them. This vision of a gentler galaxy has profound implications for the greatest question of all, the question of life. The central theory of panspermia is that life is not a local phenomenon, but a galactic one, with its seeds, the complex organic molecules necessary for biology, transported from star to star on the backs of comets. Our old view of a purely violent galaxy made this a difficult proposition. How could the delicate, complex molecules of life possibly survive the brutal ejection and the harsh interstellar journey? But if a structure as enormous and as fragile as the comet 3I/Atlas can survive, then the microscopic, resilient organic molecules frozen deep within its core would be even more likely to endure the trip. The gentle ejection process that we have theorized would protect them from the initial cataclysm, and the comet's own fluffy, porous body would act as a perfect sacrificial shield, its outer layers absorbing the radiation and the impacts, while the precious cargo in its heart remains deep frozen and safe. The improbable survival of this one, fragile ghost, has in a strange way given us a new hope. It has replaced our vision of a purely violent cosmos with one of subtle complexity, of delicate exchange. It suggests that the materials for building worlds, and perhaps the materials for sparking life, are not just being blasted across the void in a chaotic hail of shrapnel. They are being carefully and gently delivered. The galaxy is not just a shooting gallery, it is a garden, and we are only just beginning to understand how it is sown. For every interstellar visitor that has graced our skies, for every message in a bottle that has washed ashore on our celestial beach, another has been sent out. The great galactic river flows in two directions. Our solar system was not born in peace. It was born in a gravitational storm, a chaotic whirlwind of creation and destruction. And that storm, in its fury, cast trillions of its own children out into the galactic sea. We have lost an entire family of comets to the void. These are the lost siblings of 3I/Atlas, the forgotten wanderers of our own home. The evidence for this great exodus is written into the very architecture of our solar system. The models of our formation, which so accurately predict the orbits and locations of the planets, tell us a violent story. In the early days, the giant planets Jupiter and Saturn migrated through the solar system. their immense gravity acting as a great cosmic shepherd, herding and scattering the trillions of smaller icy bodies that filled the primordial disk. Some were herded into the stable pastures of the Kuiper Belt, beyond Neptune. A far greater number were flung out into the vast spherical halo of the Oort cloud, a trillion-strong ghost army of comets that still surrounds us. But the models are clear on one startling point. For every one comet that was successfully placed into the Oort cloud, 4 or 5 more were thrown too hard. They were given a gravitational kick, so powerful that they achieved escape velocity, breaking the sun's leash forever. Our young solar system was like a cosmic volcano, erupting not with lava, but with comets, blasting quintillions of them out into the interstellar medium. We have sent out far, far more messengers than we have ever received. Somewhere out there, at this very moment, a comet made from the same primordial ice that would one day form the oceans of Earth is passing silently by a star in the constellation of Orion. A fragment of our own home, a lost sibling, is now an interstellar visitor in another alien solar system. It is a humbling thought. We are not just a port of call on the interstellar highway, we are one of its greatest exporters. For a long time, the fate of these lost siblings was a complete mystery. How could we ever find them, scattered as they are across the immensity of the galaxy? The answer, remarkably, comes from a stellar graveyard. It comes from studying the ghosts of dead stars, the white dwarfs. These are the dense, smoldering cores left behind when a star like our sun dies. Their atmospheres should be pristine, made of pure hydrogen and helium, but we often see them polluted, tainted with the heavy elements of rock and ice. These dead stars are cosmic vampires, feeding on the asteroids and comets that fall into them. They are planet eaters, and by studying the light from their polluted atmospheres, we can perform a stellar autopsy. We can read the chemical fingerprint of the object the white dwarf has just consumed. The galaxy is a graveyard, and the white dwarfs are the tombstones. By reading their inscriptions, we see the chemical ghosts of shattered worlds. Some of these ghosts have a composition that looks just like the asteroids from our own solar system, but many are strange, with bizarre chemical ratios that have no equivalent in our home. These stellar autopsies are an independent confirmation of what the interstellar visitors are telling us. The galaxy is filled with a wild and wonderful diversity of planetary materials. We are all part of a great cosmic exchange, a ceaseless, billion-year-old cycle of creation, ejection, and consumption. Our journey into the improbable life of 310/Atlas has led us to a startling and beautiful vision of a gentler galaxy, a cosmos more capable of forming, ejecting, and transporting delicate life-bearing materials than we ever thought possible. This should be wonderful news for the prospect of life beyond Earth. It should mean that the seeds of biology, the complex organic molecules carried within these comets, are widespread. The galactic garden, it seems, should be well and truly sown, and yet this hopeful vision only makes the great cosmic silence more profound, more deafening, and more deeply unnerving. This is the Fermi paradox, the stark contradiction between the high probability that life should be common and the utter, echoing lack of any evidence for it. No signals, no probes, no artifacts, just the cold, indifferent static of the universe. The story of 3I/Atlas pours fuel on this paradoxical fire. If a celestial snowflake can survive an interstellar journey, then the panspermia hypothesis, the theory that life itself can be transported between the stars, suddenly seems far more robust. The galactic garden should be in full bloom, so where are all the other gardeners? The silence becomes harder, not easier to explain. But perhaps the strange story of our fragile ghost also offers us a new and subtle clue, a possible solution to the paradox. Its survival, as we have theorized, was not an everyday event. It may have required an entire chain of improbable circumstances, a perfect storm of cosmic luck. Think of it like trying to send a fragile, hand-blown glass sculpture through the global postal system. The vast majority of the time, no matter how well you pack it, it will arrive shattered. The journey is simply too rough, but perhaps, just perhaps, if the sculpture is made with a uniquely shock-absorbent type of glass, its inherent composition, and if it is packed in a very specific and unusual fluffy material, its porosity, and if it is sent from a post office that uses a uniquely gentle, multi-stage delivery system, the gentle ejection, then it might, just might, arrive intact. What if the transport of the essential ingredients for life is like this? Not a common everyday delivery, but a rare specialized white glove service that requires an entire suite of just right conditions. What if the successful seeding of a planet requires a fragile, porous carbon poor comet, born as a shard of a differentiated world, from a solar system with a rare planetary architecture that allows for a gentle, multi-stage ejection? The survival of 3/Atlas in this light may not tell us that the galaxy is uniformly gentle. It may tell us that the galaxy is a place of extreme and violent contrasts, with vast destructive regions and tiny, almost impossibly rare pockets of serenity where the conditions are just right. Perhaps the specific combination of circumstances needed to both create and successfully transport the seeds of life is so fantastically rare that the number of truly life-bearing worlds is far, far smaller than we have ever imagined. The ghost has given us a clue, but we do not yet know if it points toward a galaxy teeming with life or a galaxy of overwhelming and profound loneliness. In the end, what is the final message of this fragile ghost? It did not arrive bearing greetings from an alien intelligence. It did not carry a golden record on its side or a map pointing back to its lost home. Its message was far more subtle and far more profound. The message was in its journey. The message was in its weakness. The message was in its death. 3/Atlas has been a great and humbling teacher. In its brief passage through our lives, it has torn up our textbooks and forced us to start again. It presented us with a paradox, a fragile object that completed a brutal journey. And in trying to solve it, we have been forced to imagine a universe far more complex and creative than we knew. We have had to theorize about gentle births in serene solar systems, about worlds made of exotic frozen gases, about world-shattering collisions, and about celestial fluffballs shielded by their own emptiness. It has connected us to the other interstellar visitors, helping to weave their disparate stories into a single, coherent narrative. Oumuamua broke our rules about shape and motion. Atlas broke our rules about strength and survival. Together, they have shown us a spectrum of strangeness that hints at a galaxy filled with objects and processes that we are only just beginning to conceive of. We are like ancient cartographers, standing on the familiar shoreline of our own small island, trying to draw a map of the entire world. We sketch in the details we know, and then we confidently fill in the great blank spaces with monsters and assumptions. And every so often, a strange and unexpected piece of driftwood washes ashore, made from a type of tree we have never seen, carved with tools we do not recognize. And in that moment, we are forced to confront the true scale of our own ignorance. We must erase our monsters, tear up our maps, and start again. These interstellar visitors are that driftwood. They are a constant, humbling, and beautiful reminder that our map of the universe is not finished. It has barely even begun. The ghost is gone. Its frozen, shattered fragments have long since dispersed into a thin, invisible cloud of dust and gas, continuing their patient journey out of our solar system, back into the interstellar ocean, never to return. But it has left a permanent mark on our science and on our imagination. Its legacy is a new sense of wonder and a new, more profound sense of our own ignorance. It did not give us easy answers. It has left us with better, bigger, and more beautiful questions. And it has left us with a keener awareness of the vast, complex, and mysterious universe that still waits patiently to be discovered. We have spoken at length of this visitor's impossible journey through space, a voyage that crossed an almost meaningless number of miles. But in our focus on distance, we have not yet truly grappled with its equally profound journey through time. 3/Atlas was not just a visitor from another place. It was a relic from another epoch. It was a physical piece of the deep past, delivered directly to our doorstep. When our telescopes look out into the cosmos, they are looking back in time. A light from a star, a million light years away, has been traveling for a million years to reach us. We see the star not as it is, but as it was, a million years ago. That light is an image of the past. But 3/Atlas was different. It was not an image, it was matter. It was a tangible, physical artifact that had completed that same million-year journey. The most powerful way to understand this is to think of it as a cosmic fossil. When a paleontologist in a desert unearths the fossilized bone of a dinosaur, they are holding in their hands a piece of a world that is gone forever. They are touching the ghost of an animal that lived in a landscape that has long since vanished, under a sky that held different stars. The fossil is a direct physical message from a lost world. 3/Atlas was precisely that. Simpias C. besis was a chemical fossil, a perfectly preserved sample of the protoplanetary disk that swirled around its parent star millions or perhaps tens of millions of years ago. The star it was born around may now be a cold, shrunken white dwarf. The planets of its home system, if they ever fully formed, may have been consumed in their star's death throes, or rearranged into a completely different architecture. The violent, chaotic period that created and ejected this one small comet is an era that is long, long over. It was a message sent from a world that in all likelihood no longer exists in the form it was in when this journey began. Let us try to anchor this in the timeline of our own world. If this object traveled for 10 million years, then when it was cast out from its home, the great continents of our Earth were still drifting into their modern positions. The ancestors of humanity were just beginning their evolutionary divergence from the other great apes. The entire history of our species, of our art, our science, our civilizations, is a microscopic sliver of the time this one, lonely object spent in the silent, patient darkness. We did not just meet a visitor from another star, we encountered a ghost from another time. Its quiet, gentle dissolution in the warmth of our sun was the final fading whisper of a story that began in a time before our own species could even dream of the stars. It is a humbling and awe-inspiring reminder that the galaxy is not just vast in space, but ancient in time, and that its immense, deep history unfolds unseen all around us. In the year 1990, a small robotic spacecraft called Voyager 1, and at the very edge of our solar system, turned its camera around for one last look at its home. The image it took has become one of the most iconic in human history. In that picture, the Earth is not a swirling blue marble, it is a tiny, barely perceptible point of light, a single pixel, suspended in a scattered sunbeam. The astronomer Carl Sagan called it the pale blue dot. For a generation, that image has defined our cosmic perspective. It was a portrait of our profound and humbling isolation. It taught us that our world, with all its triumphs and all its tragedies, all its art and all its wars, is just a lonely mote of dust, adrift in a great, dark, cosmic arena. For 30 years, this has been our story. We were the sole inhabitants of an isolated island, separated from all others by an ocean of vacuum so immense it seemed utterly uncrossable. The interstellar visitors, the strange needle of Umumamo, the familiar comet of Borisov, and the fragile ghost of Atlas, have not erased that image, but they have given us a new one to place alongside it. The pale blue dot showed us our physical isolation, but the interstellar highway has revealed our profound material connection. We are not an island sealed off from the rest of the cosmos. We are a port city. The ocean is not empty, and our shores are constantly being washed by the currents that flow between the stars. If the pale blue dot was a photograph of our lonely island home, then the discovery of the interstellar highway is the moment we walked down to our beach and found 1,000 ancient foreign artifacts washed up on the sand. It is the moment we realize that our island is not alone in the ocean, but is constantly being visited by the currents that connect all the lands. This new reality changes our relationship with the universe. We have long known, in an abstract way, that the atoms in our bodies were forged in the hearts of stars that died billions of years ago. But this is a distant ancestral connection. The interstellar visitors show us a connection that is far more immediate, far more intimate. The water that fills our oceans, the complex organic molecules that may have been the very spark that ignited life on this planet, may have been delivered here by visitors just like these. Our home, our biology, our very existence may be a hybrid, a fusion of local materials and alien imports. The story of 3I/Atlas has redefined our home. We are still on that pale blue dot. It is still the only home we have ever known, but it is no longer a lonely dot. It is a connected dot. It is a busy port of call, a crossroads on a galactic river, forever linked by invisible currents to every other star system and every other world in the great cosmic sea. Our journey with this fragile traveler is now at an end. We have followed its ghost from its baffling death back to its impossible birth. We have woven a story of survival, a tale of a celestial snowflake that crossed a cosmic firestorm. But in solving one paradox, we have uncovered a dozen new mysteries. We are left, as all great explorations leave us, standing before an even larger and more profound ocean of the unknown. We are left with the unanswered questions. What, truly, was the secret of Oumuamua? Was it a nitrogen iceberg, a shard of an alien Pluto, as the theories suggest? Or was it something else? A mystery so deep that we have not yet even conceived of the right questions to ask. What kind of serene and exceptionally rare solar system both created the fragile ghost of 3I/Atlas, and then possessed the gentle, complex machinery to eject it without shattering it? And how many of these gentle gardens exist, hidden among the violent factories of the galaxy? Is the galaxy a gentle place or a violent one? Or is it both, a place of extreme contrasts? And did we, in witnessing the arrival of 3/Atlas, simply witness a miracle of survival, a one in a trillion shot that happened to land on our doorstep? Are we, in the end, truly alone in a galaxy that seems so perfectly and so gently designed to share the seeds of life between its stars? Or is the silence we hear a mystery of a different kind? A silence not of absence, but of our own inability to listen. And the final, most tantalizing question of all: what other phantoms, what other messengers are sailing toward us now, out there in the unending dark? What new paradoxes, what new impossibilities are on their way to our shores, carrying the answers to our questions, or perhaps just carrying even deeper and more beautiful mysteries? We began our journey tonight with a paradox, the mystery of a fragile traveler that completed an impossible journey. We end it with a new vision of the cosmos, a vision born from the dust of this one shattered visitor. That faint smudge of light, which we named 3I/Atlas, was a teacher, had led us down a winding path, from its gentle death, back through the hostile void to the violence of its home. In trying to understand its weakness, we were forced to imagine a universe of surprising strength. In trying to understand its survival, we were forced to imagine a universe of surprising gentleness. We thought we were studying a single strange comet, but we were in fact learning about the very nature of the galaxy itself. The ultimate message of this fragile ghost was not in its carbon-poor chemistry or in its hyperbolic path. Its final and most profound message was its survival itself, however improbable, however lucky. Its journey was a quiet and yet irrefutable demonstration that the great chasm between the stars is not an uncrossable barrier. It is a river, and on this river, the traffic flows. The galaxy is not a disconnected collection of isolated islands. It is a single, unified place, a place of constant and subtle exchange, a place of deep history and of profound and largely untapped mystery. Tonight, when you look up at the star-filled sky, know that you are not looking at a static photograph of distant, lonely lights. You are looking at the surface of a deep and ancient river, an unseen river, flowing with the ghosts of other worlds, the fossils of other times. They are the shrapnel of shattered planets, the primordial leftovers of creation, the gentle snowflakes from serene gardens. They are sailing past you, even now in the silent darkness between the stars you can see. Then we, a curious species on the shore of this one small world, for the first time in our 4.5 billion year history, are finally learning how to see them. Our journey has just begun.